let us leave the ocean currents and talk about two phenomena in the ocean with which you're probably a lot more familiar, and these are the waves and the tides. And of course you can observe them if you just stand on the shore. Now the waves, of course, are very important for sedimentary processes, and we should say the tides are important if you're going swimming. In certain areas one doesn't go swimming unless the tide's in. The tides, of course, have been known since the earliest of times. They were known by the navigators in the Mediterranean and by the English navigators and by any seafarer who put into port, not only because of the rise and fall of the sea surface, but because there were also currents created in narrow channels which were very hazardous to navigation. Even though it was possible to predict the tides in the 12th and 13th century, an understanding of the tides was not arrived at until, in fact, Sir Isaac Newton discovered the force due to gravity. And the reason, of course, is that the tides are caused by the gravitational pull of the moon and the sun on the water surface of the Earth. The earliest theories were called the equilibrium theory, and to begin with we'll imagine that the Earth is rotating and that it is completely covered with water, and look at what are called the tide generating forces. Now here we have the Earth in this diagram in the center, and we imagine that we have a thin skin of water over the Earth, and we have the moon, which is circulating around the Earth rather slowly, and then we have the Earth spinning very much faster than the moon. Now, in fact, the Earth and the moon spin together about a common center of gravity, and this causes a centripetal force on the water which is constant over the surface of the Earth. This is the force that you observe when you are twirling a ball on the end of a string. The other force, of course, is the force of gravitation. The moon exerts a gravitational pull on the water on the surface of the Earth. Now the centripetal force is constant, directed away from the moon over the surface of the Earth, but the gravitational force of the pull of the moon on the Earth and on the waters on its surface depends on the distance. The further you are away from the moon, the less the moon's gravitational pull is. The result of this is that on the side of the Earth nearest the moon, the gravitational pull of the moon is greater than the centripetal force, and on the point of the Earth farthest away from the moon, the gravitational force is a little less. Now these two forces then interact, and we have a resultant force, and if we look at the equator, there'll be a resultant force on the water, on the side nearest the moon towards the moon, and there'll be a resultant force away from the moon on the other side. And these will operate around the surface of the Earth, and the net effect is to pull the water of the Earth out into the shape of a football, like we have indicated. There'll be a bulge on the side nearest the moon and a bulge on the side furthest away from the moon. Now, of course, the Earth is rotating, and if we can now imagine that there is no friction between the water and the Earth will rotate. So in effect, these bulges will travel around the Earth, and these cause the tides. And these two forces we have described are the tidal generating forces. Now, using this simple theory, we can immediately see why we have high tides called spring tides and rather low tides which are called neap tides. This is caused because not only the moon exerts a force on the water, but also the sun does too. It exerts a gravitational force, and the even though the Sun is a very much larger body than the Moon and the gravitational force due to its size could be much stronger, it's much further away. And so in fact the gravitational pull of the Sun is a little less than half that of the Moon. Now we must remember that not only does the Earth spin, the Moon rotates around the Earth, but we also have the Earth gradually precessing around the Sun. And every so often, about twice a month, the Moon and the Sun are in line with the Earth. So here we have the Earth, the Moon, and the Sun. Now when this occurs, the pull of the Moon and the Sun on the Earth reinforce one another, so the bulge, which is caused by the gravitational attraction, is quite large. This also occurs when the Moon is in opposition to the Sun, that is at a full moon, and you also get the same effect. Now when this occurs, one gets quite high tides. At another period of the Moon, when the Moon is in quadrature, halfway through its passage, we would have the Moon either in this position or in that position, and we'll have the Sun here. When this occurs, of course, the Moon is trying to pull the water towards it, and the Sun is trying to pull the water at 90 degrees. And instead of a very large bulge, the bulge is very much lessened. And of course, to an observer rotating on the Earth, the actual tides will be much smaller. These are called spring tides in the case of when the Moon and the Sun reinforce one another, and neap tides when they are in quadrature. And the spring tides occur in new moon and in full moon, and the neap tides when in between the two. Now, of course, this means that with the Moon we get 2 tides a day. Now, because the Moon is rotating about the Earth as well as the Earth spinning, it turns out that these tides aren't exactly every 24 hours, but are every 24 hours and 50 minutes for 2 tides, so we'll get 1 tide every 12 hours and 20 minutes, so that the tide gradually gets a little later and later due to the precession of the Moon around the Sun. And there are other effects to be taken into account, since the gravitational force depends on the distance between the Sun and the Moon. When the Moon is nearest the Earth, the tides will be larger than when it's further away, and similarly when the Sun is nearest the Earth, the tides will be larger due to the Sun. Every so often, about every 400 or 500 years, it so happens that the Moon and the Sun are lined up. They are at their both of them are at their closest to the Earth. They're also lined up with the equator, and then we would in fact get the largest tides of all. The last one happened in around 1400, and the next one won't happen for another 3,000 years, so I don't think we need worry that we'll be here when we have one of these very large tides. Now, the one thing we must take into account now is that the Earth isn't covered with water, and in fact the Earth is spinning, and it has land masses which get in the way. And if we could look at the globe for the moment, we would see that there's the Atlantic Ocean bounded by the Americas, and there's Pacific bounded by the Americas and Asia, and there's the Indian Ocean. And the effect of these boundaries have a pronounced influence on the actual tides that we see. To understand this, let's first look at a tide in a narrow channel. Here we have a diagram which illustrates a channel. This is the entrance, and this is the top of the channel. And on the ingoing tide, as the tide moves into the channel, there will of course be a force directed to the right, and this is our now familiar Coriolis force. And the Coriolis force will cause the water to tilt up to the right on the ingoing tide. Now, on the outgoing tide, the water is now going out of the channel, and the Coriolis force still acts to the right, it would act to the left in the southern hemisphere, but we'll assume we're in the northern hemisphere, and it would in fact cause, again, the water to tilt up to the right. Now, the effect of this is that on the right-hand side of the channel, we'd have rather a large tidal range, and on the left-hand side of the channel, we would have a narrow tidal range, because remember, when the outgoing tide, the water level is in fact lower. I've indicated the water level by this dotted line. Now, this, if this channel was wide enough, this would in fact give rise to a sort of circulatory tide in the basin due to the Coriolis force. Not only that, we find that at certain points in the basin, we have what are called nodal points. Now, let's look at this simple diagram to explain very simply what a nodal point is. If we have a basin, as I've illustrated with the black lines, and we have water which banks up to the right and then to the left, we would find that in the middle of the basin there would be actually a place where the water level remained the same, so that the water would actually sort of slosh to and fro like this, but in the center it would remain the same. Now, if we could imagine in a place like the Atlantic a circular tide, as it is called, as I've illustrated in the previous diagram, we would find that the tide progressed around the Atlantic Ocean, and at certain places, depending on the geometry of the ocean, there would in fact be what is called one of these nodal points. Now, this diagram actually illustrates the progression of the tide around the Atlantic Ocean. In the center, well, a little towards the west, off Newfoundland, we have one of these nodal points where in fact the water doesn't rise and fall at all. And at 0 hours, at a particular time called 0 hours, this line would indicate the position of the high tide. At 2 hours later, the high tide would be here, 3 hours, 4 hours, 6 hours, 8 hours, 10 hours, 12 hours. So an observer on the coast would in fact see the tide progressing past him. There are quite a few of these nodal points in the ocean. They're quite difficult to calculate, and but generally they are accurate enough, and using them, tides are in fact predicted. Now, to come back to this tides in channels again, there's another phenomena which occurs in a channel, and it's called resonance. And if the tide moves in and out regularly, as it will, according to the movements of the sun, and the length of the basin is such that just when the tide moves out, the tidal wave moves up the basin, it's reflected from the end, and of course it will move out again. And if this coincides with the natural period of the moon, you'll get rather high tides. Now, you can demonstrate this effect to yourself in a rather simple way in your bathtub. If you move your body backwards and forwards, you'll create a wave moving backwards and forwards in the bath. And if you time it exactly, if you time your movement of your body so that when the water is reflected from the end, it is moving back just as you push your body back, and you wait till the water comes forward and move it forward again, you can get rather a large oscillation going in the bath. In fact, you can slosh the water out of the bathtub if you become adept at this. But if you move your body at a certain speed which doesn't coincide with the natural oscillation of the water in this bathtub, then you'll only get little waves. And this creates very large tides in certain areas of the world. And one of the most famous of these, of course, is the Fundy Tides. They can be very high, up to 40 feet. And over here we have a picture of one of our research vessels from the Bedford Institute of Oceanography, which is in the Bay of Fundy, and it has been left high and dry by the receding tide. The level of the tide when it is fully in is at the termination of this dark point in the on the wharf. This, of course, is one of the reasons that the people are very interested in generating tidal power in the upper reaches of the Bay of Fundy, because of the very large tidal ranges generated by the effects of this resonant effect. In the open ocean, of course, the tide it varies in heights, but it is only about 1 meter, and it isn't noticeable. Now, not only in these channels do we get this type of effect from the tides, but we can also get a phenomena called a tidal bore. And this occurs when the water suddenly shoals, and the tide then can create a wall of water which moves into the inlet, and again, this can be observed in the Bay of Fundy, up the Petitcodiac River. And this is a picture of the tidal bore. The bore is about 1 foot high, and this is the beginning of the incoming tide. Now, for tourists, one of the nice things about this particular bore is it can be predicted very accurately. The reason the tides can be predicted accurately, of course, is because they depend on the motion of